So I'll just briefly introduce Josh's talk. Josh, basically I've known Josh since he got here. I was his undergraduate advisor from the moment he came in and confided in me that he really had no interest in geology whatsoever, but he did want to get a job. And this seemed like one way to do it. And what's been really cool, I mean, Josh has obviously been a dedicated student. What's been really cool for me to watch over the last couple of years is how much he's grown to love this new topic. And so this project that you're going to see today is something that started when I was headed out to Wyoming to work on some stuff, and Josh and Blake Roberts, who a lot of you guys know, came out with me to do field work, and Josh got interested in this as we were out there, and eventually decided he wanted to take it on as his senior research project, which there's a lot of trust in me because I'd never done one of these before, so I appreciate that. Josh is going to impress you, I hope, with the stuff that he's done. What I just thought I'd mention briefly is the stuff that you don't see here, that those of you who have done research projects kind of appreciate, which is all of the grunt work that goes on behind the scenes. What you're not going to see here are the hours and hours and hours of rock cutting and chopping and grinding and dissolving and hours of fruitless searches in the library trying to find a piece of literature that you couldn't find and so forth. And all that's been distilled out of this talk, but for those of you that have done some research realize that there's always a lot more that we see, and every data point is hours and hours and hours of work. So with that said, I'm going to let Josh tell you about Southeastern Wyoming.
Y'all ready for this? Can you time me? So like Dan said, I'm Josh, and I've been working with Dan since last summer, so almost a year now. And we titled this project Using Geochemistry of Mafic Igneous Rocks to Understand the Tectonic Origin of Barber Lake rock. Now I chose this picture just kind of give you an idea of how complicated subduction zones and arcs and back arcs can be. And also because I like that. So the problem I'm going to try to explain to y'all is somewhat complicated. So the first third or so just of the talk itself is just going to be setting up the problem. Okay, so to understand this problem, you need to understand kind of like how North America was assembled. So broadly speaking, you have this Archean core, pieces that are older than 2.5 billion years old. And I've kind of highlighted them above this red line here. So pieces like the Wyoming, the Superior, and the Hearn. And then the rest of North America seems either grown in place or created in this like southeasterly direction. So the Central Plains area here is 1.8 to 1.6 billion years old. The Grenville is about 1 billion years old. And then the Appalachians came, and on the west, the Cordillera. Now, to be a little bit more clear, that the idea is that we didn't have this Archean terrain, and then another continent, our little continent came in and collided and created this mega continent of North America. The idea is that about 2 billion years ago, Wyoming was a beach, southern Wyoming was a beach, so there's a subduction zone there. And these are little arcs. And through time, these arcs have accreted, and they've accreted. And they created, then some plutons come in, and as you can see, it's growing in this southeasterly direction. What we are particularly interested in is this contact right here between the Archean terrain and this early Proterozoic stuff. There's been sediments dated there about 2 billion years old. The arc directly to the south is about 1.8 billion years old. So there's about a 200 million year old gap where we don't know what's going on. So if I zoom in on that contact, here's that contact right here. This is the Archean stuff. This is that early Proterozoic stuff. If you see, this contact here is called a suture, the Cheyenne belt. And you see here, it's pretty simple, just a nice clean contact. But over here, it's a composite suture. You have these blocks separated from myelinite zones. These are shear zones all through here. Now, the upper block, the Barber Lake block, is pretty simple. It's interpreted to be a piece of this Archean stuff that got thrust up onto the continent. The Barber Lake block, though, is not as easily understood. So if we were to take a slice out of the Cheyenne belt right there and look at it in a cross section, this is what it would look like. You have this Archean basement to the north. Here's that thrust up piece that I said, the Barber Lake block. Here's the arc to the south, and the Barber Lake block is sandwiched between them. Now the geology of the area, is the Barber Lake block is primarily granitic gneiss, and the Green Mountain Arc is a bunch of volcanic rocks. The Barber Lake block is primarily a metasedimentary sequence with some amphibolites in there. Now, Duberdorfer and Houston have proposed a model based on those rock types alone. They saw that the Barber Lake block looked like an arc-related basin in a tectonically active environment. So they proposed the idea that we had the arc in the south and a subducting slab in the Archean crust to the north there. Now, a way to test this model would be to actually date the rocks. And you can do that by neodymium model ages. So what are neodymium model ages? Well, let me go ahead and explain this graph first. This is today. So on the x-axis, this is today. That's 4 billion years ago. And on the y-axis, we have neodymium 143 and neodymium 144. Now, neodymium 144, the amount of neodymium 144 has not changed throughout Earth's history. It's been the same as today as it was 4 billion years ago. Neodymium 143, on the other hand, we actually have more of that due to the radioactive decay of samarium. So the idea here, the ratio is going to get larger as more neodymium 143s is created. So if we were to melt the upper mantle right here, it would take this trajectory, the ratio would. And then today, we can take that rock, grind it up, and backtrack to see where it crosses that line. Come down, and we get an estimated age. For example, this one would be about 1.8 billion years. So this has been done by Ball and Farmer, and they found that the Green Mountain Arc had an age of about 1.78. The Archean Craton had ages greater than 2.5. And the Barber Lake block had ages between 2.1 and 2.5 billion years. Now, they interpret this as making sense with this model, because if you had some of this arc stuff weathered, the igneous stuff would weather and erode and deposit into the basin, and maybe some of the Archean stuff eroded and weathered into the basin, you would get a number somewhere between there. Now, that was just an estimate. A more precise way to date the Barber Lake block would actually be dating the sediment itself. They couldn't do that back then, but now due to the advent of ICP-MS, you can actually date individual grains of zircons and get a more precise age. So what are zircons? For those of you who don't know, it's a very small mineral. This picture here is 50 microns, so it's about 1/20th of a millimeter. Zircons are a very hard and durable mineral. They're resilient during metamorphism, and within them they contain uranium and thorium that can decay into lead, and that can be used as a clock. So by obtaining the Barber Lake detrital zircon data, we can actually test this model. This has been done. But if we look at this model, we would expect that the igneous zircons would erode and they would be deposited. And the igneous zircons from the Archeans would be deposited here. And we would get a bunch of 1.78 billion year old zircons, and we would get maybe some 2.5 or greater year old zircons. So this is a distribution graph. So the idea here is wherever it peaks, there were a lot of zircons of that age. Wherever it tapers off, there's little to no zircons at that age. So this black line here, you see it peaks right here about, it's like 1.87 billion years. Then it tapers off. Then we have this little hump over here. That would be the age of the Wyoming province, to the north, the Archean stuff. This red bar is the age of the igneous age of the Green Mountain Arc, 1780. Now, if you remember on the previous slide, I said we had assumed we were going to have a peak at 1780 from the Green Mountain Arc. But instead, we have this peak here at 1.87, a number I've never even mentioned. So if we go back to that model, there's some problems. First, there's no Green Mountain Arc detritus in the Barber Lake block. Second, there is no local source for the 1.87 billion year old zircons. So what this suggests is that this model just doesn't work. Now, the question is, so the next question was, where did the 1.87 billion year old zircons come from? So if we zoom out, looking at North America, we look over here in the Great Lakes region, there's this Pinokian terrain. The Pinokian terrain is about 1.88 to 1.86 billion years old, which correlates with the Barber Lake block's detrital zircon data. So before I get into our hypothesis is that the Barber Lake block came from the Pinokian. before I get to that, I'm going to talk about the rocks that we collected in the Barber Lake block. If you remember, I said that there were a bunch of metasedimentary rocks that had some amphibolites within them. We interpreted those amphibolites to be metamorphosed basalt dikes. So when we collected those, we wanted amphibolites because amphibolites have, they're typically metamorphosed basaltic rocks, basalts, gabbros, and those form from a magma from the mantle. Now, in different tectonic environments, will produce a different chemistry in the melt. So you can look at the chemistry of the basalt and figure out the tectonic origin. I didn't have rocket pass around. So the first thing we did was look at these in this section, and the reason we did this is because typical modal mineralogy, the typical composition of a metamorphosed basalt will have a lot of horn-blended plage. And that's what we see here. We have all these brown and green grains here. There's the 6120 cleavage of hornblende. You see a lot of hornblende in here. Of course, you probably don't, whoever has mineralogy optics, that could be quartz. But in XBL, you see that it has albite twinning. So that identified that we do have a lot of hornblende, we do have a lot of plage. So therefore, it kind of supports the idea that our field interpretations are correct, that these could be a metamorphosed basalt dike. Another reason we wanted to look at this in thin section was to see the geochemical alteration, because that would tell us how reliable the geochemistry is when we get it back. And as you can see here, it's really not altered that bad at all. So the next question that we had was, one, are these related? We gathered these throughout a very large area in Barber Lake block. So we want to know if they're geochemically related at all. So one way to do that is to plot these on a bunch of different diagrams. First diagram we plotted on was a rock classification diagram, just to see if it did have the chemistry of basalt. And if you see here, 4 of them actually plotted directly in the basalt field. And we have this little outlier here. It's called a picrobasalt. And a picrobasalt is basically a basaltic rock with a lot of olivine fibrils. So there's a lot of olivine crystals in there. The next diagram we plotted on was to kind of give us an idea of maybe the tectonic environment. This is the AFM diagram. And the idea here is a alkaline basalt is typical of like island arcs, and a foliatic basalt is typical of like a rifting environment. If you notice, these 3 here cluster together. Now we have 2 outliers. I'll get to that on the next diagram. So here's an element versus element. It's magnesium versus iron. You see, we set up these 3 that cluster together, and we have these 2 outliers. And the reason that, these are all different samples, but the reason that these 3 look the same is because after plotting these on like tons of element versus element diagrams and discrimination diagrams, these always plotted as a cluster. So just to simplify things, we made up the same zone. These 2 here were always an outlier. They always seem to go in their own direction. So the next question is, can you have related rocks and yet still have an outlier? The question is, the answer to that is yes, through crystal accumulation. So for those who don't know what crystal accumulation is, this is a magma chamber. These are little crystals that are forming and settling out of that magma chamber. Now, the more minerals that collect in the rock becomes, the chemistry of that rock becomes more like the mineral and less like the magma. So a way to test this is to plot these on various element versus element diagrams. And if you notice, MD160 is way up there. A lot of magnesium and a lot of nickel. What mineral do we know that has a lot of magnesium? Olivine. Well, nickel has a high affinity for olivine. It prefers olivine over the liquid. So as olivine is crystallizing, it's pulling in that nickel, causing the rock to look more like olivine's chemical composition. So we interpret this rock to have accumulated some olivine. After doing it on different diagrams, we also found out that it probably had some iron titanium oxides in it too. Now if you notice on this one, MD113, it has a lot more phosphorus and thorium than the rest. So what mineral do we know that has a lot of phosphorus in it? Apatite. So thorium likes apatite. It prefers apatite over the liquid. So as apatite crystallizes, it's going to grab that thorium. So, and causing the rock to look more like apatite's chemical composition and less like the magma. And we also found that MD113 MB113 probably had a lot of clinopyroxene that accumulated in it, and some iron titanium oxides too. So what we've interpreted MB113 and MB160 to be are accumulates of some minerals, and they don't represent the liquid composition, and that's what we want. So what we've done is we've just thrown these out, and we concentrated on the ones that we thought best represented the liquid composition of the magma. So the next question is, what's the tectonic origin? So by plotting these on different discrimination diagrams like this one, this is thorium, hafnium, tantalum diagram, basically what some smart people have done, they've gone around to arcs and ocean islands and mid-ocean ridges and collected the salts. They found the geochemistry and then they plotted it on a diagram like this, and they've outlined a region that they fell in. So then what you can do is take rocks like ours, an unknown tectonic origin, plot it on the same diagram, and see what they correlate. So if you notice, we have two that plot in the arc basalt field, one in the mid-ocean ridge basalt field, but they're still very close together, right on that boundary. If we go to another discrimination diagram, this is lanthanum, yttrium, and niobium. All three plot right on the edge of a back arc basin, but yet still in a volcanic arc tholeite and a mid-ocean ridge basalt. On another discrimination diagram, zircon versus titanium, they still cluster together, but two in a mid-ocean ridge basalt and one in a mid-ocean ridge basalt plus an island arc tholeite. Still right on that boundary. And on the last discrimination diagram I'll show you, this is titanium versus vanadium. If you notice, all three are still clustering together, and they're plotting in this mid-ocean ridge basalt back arc basin field, but bordering on the island arc tholeite. Now, if you notice, like every diagram seems to be throwing it into a mid-ocean ridge basalt or an island arc or a back arc basin. Well, back arc basin basalts, this is typical of a back arc basin basalt because its chemistry is right between a mid-ocean ridge basalt and an island arc basalt. I'll show you what I mean. So you've all seen typical subduction diagrams. It's a little cartoon. So here's the subducting slab, here's the arc, and behind that arc is a back arc basin. Now the melts form very similar to a mid-ocean ridge, through decompression melting. The difference though is that we have a modified mantle due to that slab. There's liquid melts and elements being added to the mantle. So during the initial rifting stage, it has a lot of this modified mantle in it. And then as slab rollback continues and the back arc basin gets further from that subducting slab, it starts to get more like a mid-ocean ridge basalt. So it falls right there in between. So what we've interpreted the Barber Lake blocks and phibolites to be are basalts formed in a back arc basin, and that the basalts intruded those sediments in that basin. So now if we zoom back out and we look at the Pinokian, remember that suture? It's a long strike. You notice right up here with the Pinokian. And if we were to take a cross section of the Pinokian and look at, this is the model that they presented, or they interpreted to happen in the Pinokian. You have the Superior Archean terrain and subducting slab, the arc, and then behind that arc is that back arc. Now if I zoom back to that, this area here is cut by a fault, and it's been interpreted that a piece of the Pinokian, most likely that back arc that was on that southern end, has been truncated. So what we suggest, well, let me actually show you that cross section. So here's what it would look like the cross section. Here's this superior craton, a bunch of thrust faults in it, with it. And there's that arc, and here's another terrain where the back arc, and even maybe even more, that arc would have been. You had the strike slip fault that truncated. So what we propose is that the Pinokian was actually larger than what they show, and through a significant continental strike slip fault, it was brought over and created onto the Cheyenne Belt. And then later, around 1750 MA, the Green Mountain Arc came in, and that's why we only see that little bit of that sliver that we see now. So the proposed tectonic model is basically that the Barber Lake block is a far travel terrain. It's locked with this. The detrital zircons in the Barber Lake block were sourced from the Pinokian arc, with lesser contributions from that superior, from the Superior Craton, and the amphibolites in the Barber Lake block originated in the Pinokian's back arc basin. So then the Pinokian's back arc basin was moved along that continental scale strike slip fault and sometime between 1835 and 1780. Now, we were not able to date the previous age of the amphibolites. So for future work, we would like to know the age of those amphibolites by using the endymium oblates. And I would love to thank Dan Jones for putting up with me, Cheryl for reading everything and let me work in that lab and answering all my other questions that I couldn't ask. And Blake, he was out there with us. He hauled around some rocks. And the Resources Committee of the Department of Geosciences and Natural Resources and the Honors College for helping funding this project. And references. Thank you. Water.
Any questions for Josh?
So it looks like that Pinokian's ring had to travel a long ways along that strike slip fault. Do you have any idea of distance traveled? Can you think of any other examples in tectonic history where this kind of thing occurred?
We talked about that along the west coast. There's a pretty significant strike slip fault occurring. And there was rocks in place from somewhere down south of the United States in Alaska. Am I right with that?
That's right. Yeah, probably the classic example is something called Wrangellia, which is a terrain that appears to have come in and hit somewhere in the Oregon-Washington area. It left a big chunk, which is now Vancouver Island, just off of BC, and the rest of it is parked up in northern in sort of the mainland Alaska as the Wrangell-St. Elias Range. And there are actually quite a number of examples where you have very large-scale tectonic movements of strike slip faults, and we did we basically pulled out Google Earth and we compared this to that, and it's about half of what you see in Wrangellia. The other way to go about it is to simply look at plate rates, look at the distance, and figure out how many millions of years it would take and see if you have that many.
We did that too, and it worked.
Yeah.
Any other questions? Yes.
So, do you have a fault that would have the right kinematics on it to make
Well,
it do
it's
that?
there is that fault, that margin right there, but orientations, they can't tell the direction of faulting. It's of overprinting.
So the rocks that were next to that boundary have been affected again by penetrative deformation?
Yeah.
Okay.
Essentially, the accretion of the Green Mountain Arc overprinted everything. And the Spirit Lake tectonic zone is all geophysics.
Yeah, that's what I was going to ask you if they're geophysical. Because sometimes the steepness of the boundary can help make your case, but...
Yeah, I know. That's why I asked you that question about
Yeah.
that margin. Any other questions? Y'all get it?
Yeah, actually.
Cool.
It was a good review.
Why don't you go back and look at some of your references? I went through those fast.
The samples that you collected, you said they were kind of all over the place, but, I mean, why was that?
Because the majority of the Barber Lake block is a metasedimentary sequence, and it's just we looked everywhere, and we only found a few places where they were as an outcrop.
Oh, okay.
And I mean, Barber Lake block's pretty big. We traveled everywhere.
So the three or four that were the melt, that represented the melt, were they close, were they from the same outcrop?
No, they were all different outcrops.
Okay.
Every one of them.
So they're all kind of equally spread out.
I don't know about equally, but
But I mean, well, like,
yeah, but they're definitely
there's no statistical, like,
Yeah.
relationship between where you found them and what you...
Exactly.
Okay.
Yeah. And obviously, we would love to have more amphibolites. I was hoping to have more, so we could have, kind of get an idea of what happened, but we couldn't find any. We didn't find many outcrops at all.
I was kind of hoping there'd be a few more discrimination back then.
Is there one you feel like you
Want to
left
get the
out?
point across. I mean, when I first saw that, I'm like, what the heck? You know, I expected just one region, and it kept on throwing it around. That threw me for a curveball.
I told him it wasn't allowed to put spider plugs on it.
Yeah. Or nurse distribution coefficient.
None of that,
Didn't
no.
matter.
All right.
All right, thanks, Josh.